So, for Chapter 6, we're going to be talking about energy and equilibrium. Energy is the capacity to do work. Now, work is very specific in terms of science. Work is a force times a distance. Okay? In other words, if you push an object, so here's my little guy, and I got a box, and he pushes it some distance. The amount of force needed to push that box some distance times the distance is the amount of work. Okay? And where did that ability come from? That is energy. Energy comes in two basic forms: potential energy, which is stored energy, and kinetic energy, which is energy of motion. Okay? So, let's talk about potential energy versus kinetic energy. So, I've got a hill, okay? I put a ball at the top of the hill. This ball has a potential energy equal to its mass times the gravitational constant times how high it is. That equals potential energy, okay? Now, if I push this, as this starts to go down the hill, it gets closer and closer to the absolute ground, which means H is decreasing. Since H is decreasing, potential energy is decreasing. But kinetic energy, the energy of motion, which is 1/2 mv squared, the mass times the velocity squared, is going up until the point at which the ball is on the ground. Then potential energy has been completely converted to kinetic energy. And that's where the law of conservation of energy comes in. The total energy in a system does not change. Energy cannot be created or destroyed ever. It can only change forms. In terms of chemistry, bonds are where we store potential energy. Okay? And a compound that has a lower potential energy is more stable than a compound with a higher potential energy. Now, you can think of this in terms of a really high ladder. Do you want to be the guy at the top of the ladder or the guy at the bottom of the ladder? Okay? The lower you are on that potential energy scale, the more stable you are. Now, reactions form products that tend to have lower potential energy. Okay? And this is what we say is favored. Okay? It means that if we take a look at a reaction, so energy is on the y-axis, and what we call the reaction coordinate, which is just a fancy way of saying progress of the reaction. What we're saying is that our reactants have higher energy than our products, and that tends to be favored. So going down in energy is going to be favored, which means the reaction is more likely to occur. Now, how do we measure energy? Well, we've got two different units that we're going to talk about. The calorie, which is the amount of energy needed to raise the temperature of 1 gram of water 1 degree C. Okay? And this is not the metric, okay, or what we call the SI system. That is not the unit that you would use, okay? The joule, this is what we would call the SI or the metric system, okay? Now, 1 calorie is equal to 4.184 joules. That number has to do with how water behaves with energy changes. Okay? That little delta there, that means change, in case you're not familiar with that. Now, we can also have larger units, the kilojoules and the kilocalorie. Okay? So 1 kilojoule is 1,000 joules. 1 kilocalorie is 1,000 calories. and 1 kcal is equal to 4.184 kilojoules. Now, this is also important when we talk about calories in terms of nutrition. The big calorie versus the little calorie. Big C versus little c. This is 1 kcal. The big C, this is your nutritional calorie, and the little c is your little calorie. Okay? So they're not the same unit. When you talk about calorie content in foods, you're actually talking about kcals. So what happens in a chemical reaction? So when molecules come together to react, they're going to bump into each other. And what's going to happen is some reactant molecules are going to break bonds. And then new products are going to be formed by the making of new bonds. So when we break a bond, that always requires an input of energy. When we make a bond, that always gives you energy back. So here I have, this is supposed to look like chlorine. To break this bond, or to cleave it, okay, and this is a specific type of cleaving or breaking. This is what we call homolytic cleavage. In other words, when I break that bond, one electron goes to the chlorine on the right, one electron goes to the chlorine on the left. I broke that bond cleanly and evenly, okay? To break that, I have to add 58 kcals per mole of energy. But if I make that bond, I get 58 kcals per mole of energy back, released, okay? So here's the thing. Notice it's the exact same amount of energy, because breaking bonds and making bonds is kind of like our potential energy, kinetic energy example, where all the potential energy was converted to kinetic energy. Well, if I break a bond, it's going to be the same amount of energy as if I make a bond. Now, delta H, that's supposed to be a delta, is the energy absorbed or released in a reaction. We call it the enthalpy change, or sometimes heat of reaction. Okay? Now, there are two different ways that delta H can be. It can be a positive value, and if it's a positive value, that means that energy must be absorbed. Okay? If energy is being absorbed, it's going into our system. We call this endothermic. Endo meaning in, therm meaning heat. So heat goes in. If we have a negative value of delta H, energy is being released. We call that exothermic. Exo, outside, therm, heat. So outside heat. And the value of delta H is negative. Okay? Now, that's kind of confusing unless you think of our reaction in terms of, I'm not very good at drawing, a bank. Okay? If money goes in, that's being added, right? Money is being added to the reaction. That's a positive. If money is going out, if you're drawing money out, it's being removed, that's a negative. It's kind of like accounting. Okay? So if we go back to our little chlorine molecule here, Cl and Cl. I don't know why this is all messed up, but it is. You'll notice that the enthalpy change to break it is in blue here, which means this is a positive value, endothermic. To form the bond, energy is released in red. That's a negative, exothermic. Okay? Now, these values are what we call the bond dissociation energy, or sometimes I just abbreviate it as BDE. Okay? This is the delta H, change in enthalpy, for breaking a covalent bond, equally dividing the electron between two atoms. This is our homolytic bond breaking or cleavage. Okay? Now, bond dissociation energies are tabulated. You can find a table of these things, and these are always going to be given as positive values because you're always breaking. Remember, breaking a bond always takes energy. Making a bond always gives you energy back. So if I have hydrogen and I break it into H with a dot and H with a dot, that requires 104 kilocalories per mole. If I make hydrogen from H dot and H dot, that is going to give me back 104 kilocalories per mole. Okay, remember, negatives versus positive. Endothermic, exothermic. Okay? And actually, let's talk about endothermic and exothermic just for one more second, because sometimes this gets to be kind of confusing for students. Okay? Endothermic, when heat is going in, that heat is going into the reaction. It's got to come from somewhere. It's coming from everything around the reaction. So what we would say is the surroundings get colder. The heat is being taken from the surroundings and going into a reaction. So these tend to feel cool. Exothermic reactions, however, heat is going from the reaction to the outside. These are going to tend to feel hot. Okay? So if something's exothermic, it's going to give off energy. It's going to feel hot. If something's endothermic, it's going to take in energy. It's going to feel cold or cool. Now, the stronger the bond, the higher its bond dissociation energy. And there is a sort of correlation between position on the periodic table and bond dissociation energy. That the higher up in the period, the stronger the bond. Okay? In other words, HF, fluorine is at the very top of the periodic table in the halogens. It has a bond dissociation energy of 136 kcals per mole. As you go down, you can see there's a steady decrease of energy, bond dissociation energy. Okay? So the lowest bond dissociation energy forms the weakest bond. Okay? And the highest bond dissociation energy is the strongest bond. Now, the change in enthalpy, the delta H, indicates the relative strengths of the bonds that are broken and formed in a reaction. Okay? Remember, we had our energy here and our reaction coordinate, and we said that our reactants and our products, reactions tend to favor lower energy products. Right? So that means that energy was higher, now energy is lower. That means heat went out. Okay? If heat's going out, then delta H, that value is negative. More energy is released in making the bonds than it took to break the bonds. And that means that the bonds in our products are stronger than the reactants. And I know that seems weird because they're lower in energy. But remember, low energy is more stable. More stable, bonds are stronger. Okay? So if I take methane and I burn it in oxygen, I make carbon dioxide and water. The enthalpy change for this, delta H, is negative 213 kcals per mole. Exothermic, heat is released. Well, this is the reaction in our Bunsen burners. We know that a lot of heat energy comes out from our Bunsen burner. Okay? In fact, 213 kcals per mole of methane burned. When delta H is positive, okay, then more energy is needed to break the bonds than is released in the formation. So our diagram might look something like this. Energy going up. Our reactants are lower in energy than our products. Okay? Energy is going up. That means that the broken bonds in the reactants are stronger than the product bonds because the product bonds are higher in energy. Okay? The higher your energy you are, the more stable, the least stable you are. Okay? So, if I take 6 carbon dioxide molecules and 6 waters, I make sugar and oxygen. This is photosynthesis. Okay? Well, we know photosynthesis requires energy. Energy has to go in because plants need sunlight. The sun provides the energy for plants to turn carbon dioxide and water into sugar and oxygen. The delta H for this is 678 kcals per mole heat absorbed. That's a lot of energy, okay? Because sugar molecules have a lot of stored energy. We know that. Sugar has higher calorie content than protein, okay? So there's a lot of energy inside those molecules. So just to reemphasize what we've been talking about when we're talking about delta H values, in an endothermic reaction, heat is absorbed. The delta H is positive, and the bonds broken in the reactants are stronger than those formed in the products. In other words, the products are higher in energy than the reactants. In an exothermic reaction, heat is released. Delta H is a negative value, and the bonds formed in the products are stronger than the reactants. Therefore, the products are lower in energy than the reactants. Okay? And remember, endothermic reactions tend to feel cool. Exothermic reactions tend to feel hot. Now, how does this happen? Well, for a reaction to occur, they must collide. Molecules must collide with a couple of different things. They've got to have the correct amount of energy to break the bonds. So here I've got a molecule AB reacting with C. They have to hit with enough energy so that that bond gets broken. And then that bond, the new bond, the B to C, gets formed. Additionally, the orientation of the molecules must be correct. Okay? So in this direction, the B and C have to collide. If C and A collide, nothing's going to happen. This can give you a new molecule, but only if there was sufficient kinetic energy. Okay? This, no matter how much Ke, kinetic energy, no reaction, because they don't have the right orientation in space. This is why we talk about three-dimensionality of molecules and our VSEPR structures, because we need to be able to figure out what shape these molecules are in order to understand when they collide, how do reactions occur. Alright, so this is an energy diagram. This is something we've actually been drawing, but I haven't been drawing it fully. Okay? An energy diagram has the reaction coordinate and energy going up on the y-axis. We've got our reactants and our products. The difference in energy between reactants and products here is delta H. Okay? Now there's something else here. There's the energy of activation. Okay? This is the difference between the reactants and the transition state. The transition state, what is that? The transition state is this in-between state where the molecules are reacting and their bonds are being broken and bonds are being formed kind of simultaneously. Okay? So every reaction has to have some sort of little oomph to get it over this hill, this energy of activation hill. Those reactions that don't have a big energy of activation tend to occur quickly. Those that have a much higher energy, the bigger this hill, the harder it is to get over that hill, they tend to go a little bit more slowly. Now, let's take a look at this reaction diagram. Is this an endothermic or an exothermic process? Well, how do I know? The products are lower in energy than the reactants. If the products are lower in energy than the reactants, that means that the products have stronger bonds. We know that exothermic reactions, the bonds are stronger in the products than they are in the reactants. So this is an exothermic process. So that energy of activation is the minimum amount of energy that the reactants must possess for a reaction to occur. Okay? The EA is often called an energy barrier. And as I talked about, if you have a really big energy barrier, then the reaction is going to be slow because it's harder to get across. In other words, fewer molecules are going to have enough energy to cross that barrier. Okay? But if you have a low energy of activation, then a lot of the molecules are going to have enough energy to cross the barrier. The reaction tends to be faster. And the difference in energy between the reactants and the products is delta H. And since this is a products minus reactants, so products minus reactants gives us our delta H. Okay? The products are smaller energy. The reactants are bigger energy. This is going to be a negative value. Then the energy of the enthalpy is negative 10 kcals. That is an exothermic reaction. Now, if I look at a positive endothermic reaction, in other words, we're talking about the reactants being lower in energy than the products. Take a look. The energy of activation is going from the reactants all the way to the transition state. That's a much, much larger energy of activation. So high EA, this is going to be a slower reaction. Okay? In general, exothermic reactions are faster than endothermic reactions because of the energy of activation barrier. Now, how can we speed up reactions? Okay? There are several different things that we can do to change how fast a reaction goes. Okay? We can increase the concentration of a reaction, of the reactants. Okay? If we increase the concentration, then we've got more molecules in a smaller space. More molecules in a smaller space means that there are more collisions. The more collisions, the bigger the chance that they've got the correct orientation and energy that the reaction will go and proceed. So we'd see an increase in the reaction rate. Additionally, in general, if we increase the temperature of the reaction, we're going to increase the kinetic energy of the molecules. Increasing the kinetic energy of the molecules is going to increase, number one, a couple of different things. It actually increases the number of collisions because they're moving faster. The faster they're moving, the more they're bouncing around. The harder they're bouncing around, the more chances there are that they're going to have a sufficient orientation and kinetic energy to actually for the reaction to occur. That's going to increase the reaction rate. Another thing we can do is we can add a catalyst. Okay? Catalysts speed up the rate of reaction without being changed. Okay? Catalysts do not change over the course of the reaction. Okay? Or actually, I shouldn't say that. I should say you get the catalyst back at the end of the reaction. The catalyst can actually change over the course, but it will always come back and be the same at the beginning as at the end. Okay? One of the most common catalysts that we talk about is palladium. Okay? Palladium works as a catalyst in hydrogenation. So this is a hydrogenation reaction. Hydrogenation is when we add hydrogen across a double bond. So something like ethylene plus hydrogen in the presence of a palladium catalyst will get ethane. Okay? And so you might ask yourself, well, where would I see this? Crisco. Partially hydrogenated vegetable oil. In other words, we take vegetable oils, which actually have quite a bit of these double and triple bonds, and we add hydrogen to them. When we do that, those molecules tend to be able to stick closer together, which increases their melting point. So they actually become a solid at room temperature. Okay? Now, the way catalysts work, they're all different types of way they work. But in general, they somehow lower the energy of activation without affecting the delta H. Okay? How they do it depends on the catalyst. Some catalysts work, and we don't really know why. Okay? It just gives it some other pathway for the reaction to occur, which gives you a lower energy of activation. So here we have a catalyzed versus an uncatalyzed reaction. Notice the difference in energy of the reactants and the products. That's exactly the same. Okay? Delta H is the same for both reactions. But the energy of activation of our catalyzed is lower than the energy of activation of our uncatalyzed. So however it works, that's what it does, is it changes the energy of activation. Now, it's really important that we have catalysts because most of the reactions in the human body can't occur without catalysts, okay? And biological catalysts are called enzymes, okay? These are usually protein molecules that have a very specific three-dimensional shape, okay? Now, this is kind of an old school way of teaching enzyme, how they work, and it's not exactly true. But we're not going to have to worry about it because we're worried about the chemistry behind it. So what we have is an active site, and this is going to bind a reactant. And this is very specific for the type of reaction that you're going to have. So this is going to enhance the rate, the speed at which the reaction occurs. Okay? So for example, lactase converts lactose into glucose and galactose. Okay? If you don't have enough lactase, like me, you get some really bad things happen when you actually eat lactose, okay? Because our body can't deal with the lactose, okay? But lactase isn't going to work on anything else. It's not going to work on sucrose. It doesn't work, okay? It's very specific for lactose. So what we have is we would call the key and lock. And this is my very favorite drawing that I ever do because it looks like Pac-Man to me. Here's my enzyme. There's my enzyme. If the enzyme doesn't fit into the active site, nothing happens. You have to have this substrate, the molecule you're working on, has to fit inside the enzyme in a very specific pattern, in a very specific way. So, for this enzyme, well, I am a terrible artist. What we'd look for is a substrate that looks like that. And so, Pac-Man, our enzyme chomps on the substrate, and what do we get? We get our enzyme back, because it's a catalyst. The enzyme remains unchanged. And now we get, well, maybe it breaks it into two pieces, okay? Again, not a great artist, but you get the idea, okay? So, that's how enzymes work, is the active site chomps on the substrate as long as the substrate fits in the active site. Okay? If they don't, nothing happens. Okay? And pretty much all enzymes work in this fashion. Okay? And it's actually kind of amazing how enzymes work. This is very simplistic and not really the truth. But even this simplistic model, if you think about it, if you have maybe an enzyme that looks like this, and we know that it eats that substrate. But what if we attach something else to that substrate? Perhaps we can get some new products and our enzyme back. Okay, so that's a lot of times how drug discovery works. Now you have a new thing, a new molecule that doesn't exist on what the enzyme usually works on. Anyway, beyond the scope of the importance of this, but it's just really kind of fascinating that how all this fits in with biology. All right, so now we're going to talk about equilibrium. Now, we talked about energy, which we call thermochemistry. Okay, in terms of chemistry, we call that thermochemistry. We've talked about speed of reaction, which we would call kinetics. And now we're going to talk about equilibrium. All three of these things kind of all fit together, and we're looking at this at a very high level. Okay, we're just kind of getting the basics of it. There's a lot of cool and interesting stuff that happens, but let's just talk basics. So, equilibria. Most reactions are reversible. It's a dirty little secret. Okay? In other words, they can occur in either direction. So, carbon monoxide reacting with water to form carbon dioxide and hydrogen, okay, is an equilibrium process. So, we can make products, or the products can react to make reactants again, okay? Now, equilibrium is when the rate of the forward reaction, okay, in this case making CO2 and hydrogen, equals the rate of the reverse reaction, okay, going from CO2 and hydrogen to CO and water, okay? The net concentrations of our reactants and our products do not change at equilibrium, okay? As soon as you make CO2 and H2, there's a CO2 and an H2 reacting to make CO and H2O, okay? This is what we would call a dynamic equilibrium. Dynamic. It's constantly in motion, as opposed to a static equilibrium, which is no movements happening whatsoever. Okay? So this is a dynamic equilibrium. The rate of the forward equals the rate of the reverse. That is equilibrium. The relationship between concentration and the equilibrium is given by the equilibrium constant, K. Okay? Now, we use brackets to symbolize concentration in moles per liter, moles over liters, or molarity. Okay? Molarity. And for any reaction, any equilibrium reaction, we have a general format for our equilibrium constant. Okay? So for AAs plus BBs goes to CCs and DDs, where these are our coefficients of our balanced chemical reaction. Okay? The equilibrium constant, K, is given as the concentration of the products over the concentration of the reactants. Now this is all jumbled up down here. But it's the concentration of our products, so C, the concentration of our product D, but raised to the power of the coefficients, so to the C to the D, over our reactants. The concentration of A raised to the power of A times the concentration of B raised to the power B. Okay? That is our equilibrium constant, what we would say is our equilibrium constant expression. Okay? So, if I've got N2 plus O2, this is all jacked up here, N2 plus O2, gas, making 2NO. Our equilibrium constant expression would be the concentration of our product, NO, raised to the power of its coefficient, 2, over the concentration of N2 raised to its coefficient, which is simply a 1. I'm going to put it there. We don't normally show it, but I'm putting it there for show. Times the concentration of our O2 raised to its power. Again, that's a 1. We don't normally put it there, but just for show. That is the equilibrium constant expression. Now, the magnitude of the equilibrium constant, the K, tells us about whether the reaction is going to favor the forward reaction or the reverse reaction. So if K is much greater than 1, okay, that means that there's more products than there are reactants. The numerator is larger. The equilibrium lies to the right and favors the products. Okay? If K is much less than 1, then the reactance is larger, so the denominator is larger. The reaction favors the left and favors the reactants. Okay? Now, what do I mean by much greater than 1? 2? Is 2 much greater than 1? No, what I'm talking about is usually we're talking about 100 or 0.01, okay, for less than 1. So, much larger. Now, if K is near 1, then there's an equal, there's not an equal amount, but there's a good amount of forward and reverse reaction occurring. Okay? If K is exactly 1, then products and reactants are present in the same amount. So let's take a look at this reaction. So for hydrogen plus oxygen going to water, the experimentally determined K has a value of 2.9 times 10 to the 82nd power. That is much larger than 1, which means that this product heavily favors this reaction heavily favors the product, and the equilibrium lies to the right. Well, that sort of makes sense. I don't worry about my water turning into oxygen and hydrogen on me, okay? That's not going to happen. Because the K for the reverse reaction is going to be much, 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 much smaller than 1. So the value of K, again, if K is greater than 1, the equilibrium favors the products, and it lies to the right. K is less than 1, it favors the reactants, and it lies to the left. If K is near 1, then we have both product and reactant in appreciable amounts at equilibrium. Now, we can actually calculate the equilibrium constant if we know the concentrations and our reaction. Okay? So, if I know that A2, or this should be like A sub 2 and B sub 2 goes to AB. If I know at equilibrium what the concentrations are, so A2 is 0.25 molar, B2 is 0.25 molar, and AB is 0.5 molar, and I know the reaction, I need to know what this is. This is A sub 2, B sub 2, 2AB. The way we calculate K is first we have to write our equilibrium expression. K is equal to, so this is the products, AB, raised to the power 2, because it's coefficient of 2, over A, raised to the coefficient of 1, and B, raised to the coefficient of 1. So there's our equilibrium expression. Now I just put in my concentrations. So AB is 0.50 molar, and I square that, over 0.25 times 0.25 molar, and that gives me the value 4. Okay? Now, the unit is omitted, okay? They say that the unit of the answer is always moles per liter, which is usually omitted. That's actually not true. We say that K is unitless. Okay, so 4.5 squared over 0.25 times 0.25 gives us 4.0. Okay, now what does this mean for our reaction? Well, K is around 1. Okay, K is around 1. Therefore, both the reverse and the forward reaction are pretty likely. Now, we can use this concept of equilibrium to actually help us. So, for example, the most important chemical reaction of the 20th century isn't making this miraculous drug. It isn't making all this, plastics or anything like that. The most miraculous reaction is an old reaction, and that is the conversion of nitrogen and hydrogen to ammonia. N2 plus H2 to NH3. This is actually a reversible reaction. It is an equilibrium. Okay, so we've got our arrows there. 2, 3. Now, this reaction doesn't occur very well at all. Okay? In biology, beans tend to have these bacteria that live in the roots that help convert nitrogen into ammonia. Because plants use ammonia. This is the major form that plants use nitrogen in. So that's why rotating your crops from corn and soybeans are very important, because you replenish the amount of nitrogen in the soil. But since this is an equilibrium reaction with an equilibrium constant that's not very favorable, there's stuff we can do. We can actually use kinetics, and we can use thermochemistry, and we can use our knowledge of equilibrium to make ammonia more readily available. And that is actually what happened in the early 1900s in Germany. The Haber process, named for Fritz Haber. And this Haber process allowed for the production of ammonia, which increased the ability for fertilizer. So crop yields actually went up because of the Haber process. But also, ammonia is the starting material for a lot of things that are weapons of war, such as propellants for rockets and some nasty stuff, okay? Bad things. So it's kind of interesting that this process led to an increase in population because we could feed them more readily, but also led to a major issue in World War I and World War II. Anyway, how do we use this equilibrium? We use what is known as Le Chatelier's principle. Okay? Le Chatelier's principle states that a system in equilibrium, if it's disturbed or stressed, will move the equilibrium such that it removes the disturbance or relieves the stress. Okay? And the three disturbances we're going to talk about are concentration changes, temperature changes, and pressure changes. All right, so let's talk about a concentration change. I've got CO2 plus O2 gas goes to 2 CO2 gas. Okay? What happens if I increase CO? Okay? If I add reactant. Now, since K is a constant, if I add a reactant, then the system is stressed, and in order to go back and make K a constant, the amount of products has to go up, because if I add product, remember, if I add reactant, is product over reactant. If that number suddenly becomes larger, then to go back to the value of K being a constant, this needs to change. So the reaction gets driven to the right. So if we increase CO, we're going to decrease the amount of O2 because that needs to be used up in order to make our product. And CO2 concentration will increase such that it goes back to equilibrium. If I increase a product, okay, same equation, this time if I increase the product, then K is equal to product over reactant. Then products becomes larger. That's going to force the reactant amounts to increase in order to bring K back to the equilibrium value. So the concentration of carbon monoxide and the concentration of oxygen increase. because I'm making reactants. If I remove a product, okay? So here I have the process of ethanol being turned into ethylene and water. If I keep pulling water out of my reaction, that's like removing the product. So since K, it's exactly like removing the product because that's what we're doing. Since K is products over reactants, if I'm constantly removing this, that number is going to go down, which means the reaction must shift to the right in order to keep that number up to get back to our K being a constant value. Okay? So the concentration of ethanol will decrease, the reactants goes down, but the concentration of our product here will increase, the C2H4. Okay? All right, what about temperature increasing? All right, so temperature increases. If we increase the temperature, then a reaction that absorbs heat is favored. In other words, if the reaction is endothermic, then the reaction proceeds to the right. Okay? Now, increasing temperature. This is something that's kind of interesting. We can think of heat, okay? And I'm going to use a different letter, which is Q. Heat is equal to Q. In an endothermic reaction, Q is a reactant. In other words, if I increase the amount of heat I'm adding, and by increasing temperature, I'm increasing the amount of reactant. That drives the reaction to favor the products. Okay? Or favoring the forward reaction. In an exothermic process, Q is a product. So if I increase the temperature, if Q is a product, it drives the reaction the reverse. Okay? So if temperature is decreased then a reaction that is exothermic would be favored, which is kind of funny. But if I think about it that way, if I increase temperature, I'm increasing product. If I decrease temperature, I'm decreasing product. Okay? So it's kind of a funny thing. We'll go over that at the very end here. Now, pressure changes. Pressure changes are going to change the direction that decrease the total number of moles of our system. Okay? And this only works for gases. If you change pressure on something that's not a gas, it doesn't matter. Okay? So, if I have my ammonia reaction here, I've got a coefficient of 1 in front of the nitrogen, 3 in front of the hydrogen. That's 4 total moles. On the product side, the coefficient is 2. That's 2 total moles. So increasing pressure drives you to the least number of moles. So in this case, it drives the reaction to the right. If pressure decreases, then you're going to shift to the portion with more moles. So if I decrease the pressure, the side with more moles is the reactant side, and it drives it to the left. So this summary chart is really, really important, okay? And it's actually very simple to use. For concentration changes, if we add reactant, we go to the products. If we remove reactant, we go to the reactants. If we add product, we go to the reactants. If we remove product, we go to the products. So notice, if you add something, it goes to the opposite. Add product, the opposite. If you remove something, it favors what you remove. Okay? Temperature. If you increase temperature for an endothermic reaction, it goes to the products. But for an exothermic reaction, it favors the reactants. And we can remember that again by exothermic, exo reaction, A plus B goes to AB plus heat and an endo reaction, A plus B plus heat goes to AB, it's exactly the same as concentration stuff. Okay? If I add heat to an endothermic reaction, adding reactant favors products. If I take heat away, taking heat away favors, so removing reactant favors the reactants. Okay? So it's exactly the same. If you decrease temperature for an endothermic reaction, it's going to favor the reactants. For an exothermic reaction, it favors the products. And pressure, if you increase pressure, it favors the side with fewer moles. If you decrease pressure, it favors the side that has more moles.